Good afternoon. My name is Ryan Belkoff. Today we're going to talk about the Utah back compression model. So very similar to NIOSH, of which we will go into the details and spend a lot more time, but this is a tool a little bit more simpler, very valid. So going through the details, from this Utah back compression, the basics, how to utilize this tool, when we're going to use it. These are all our objectives today. So the creator, Donald Boswick, he is retired from University of Utah. He is currently emeritus at the Department of Engineering. But back when he was doing his PhD, he was investigating this tool and creating it along with Dr. Bernard. So those two. So if you look at the date, we're looking at 2002. So it's our 2000 when this was published in between those times. So you see two different dates, I guess, on here. So they were initially publishing it in 2000 and then did a revision in 2002. And then he had a researcher, continuing his PhD. And this is several years later, about 5 years, about 2007. So all of these people, Dr. Boswick is probably the main leader of this tool. And so just some other papers with him, with the original master's thesis that really published it and got it going. So from this tool for the Utah back impression, so similar to that I said of NIOSH. So number one is distance from the person to the box at that center. So that first one here to that L5S1 vertebrae. And then, again, similar to NIOSH, but we got the vertical height from how far it is from the surface. But the third and fourth are where they add personal factors that the NIOSH lifting equation doesn't. So it equates, well, sorry, the third one equates the weight of the box, but the fourth one is where the personal factors come in. And so this is looking at the height of the worker as well as the weight of that worker to personalize it a little bit more. And so when they developed this model, the first one is how much they're bending. And so they categorized it when you see that worksheet in 3 different spaces. So as you can see, probably a third of the way down to a halfway down to 3/4, and then at 90, they were saying a complete flexion there. So this is that worksheet, so it fits on one page, similar to most of your ergonomic risk analysis that you'll be doing, but you'll see it's not as filled in. So it's looking at this first one, what are those personal factors? What is the weight of that box? And then looking at that angle between those 3. And so they say the sine, so looking at that degree. So if we were at 40 degrees, we were saying the sine is 0.64 on this one. And then they calculate that compression forces by adding all those together. So this is just a little bit more simpler, getting that personal factors, the weight of the box and the load, and then it calculates that compression. So as you can see in later slides, so we have Tom Bernard. He put this on Excel to make all these calculations, so we don't actually have to, put it in the calculator. It will do it for us. So these are some examples here. We'll go through ones that are filled out. Again, look at that Excel. So first we're going to put, the patient's, when this assessment's done with the patient's name. This top one here is that person's weight. So that we're saying 90 kilograms. So we could do this in metric or US standards, depending on what we want. The load on this one is 41 kilograms. The horizontal distance is how far it is from the ground. And so we're going to say 0.39 meters. And that back posture right in the middle at 45 degrees. And then that gives us our compression factor of 5,200. So quite a bit on this example. So let me show you more of a picture demonstration on this one. So this guy bending all the way down. So we asked the subject how much they weigh. So this guy weighs 165 pounds. As you can look at how much he's bent at a full 90 degrees there. The load of this box, even though it's very wide and awkward, is at 25 pounds. And then the last one is for that from the L4, L5 distance to the second knuckle. But notice on this example, we have it spread out. One's higher than the other one. So we're going to go through, figure out what the middle part of that is. And for this example, we're going to say 15 inches from the L4S1 L5S1 joint to that middle between those hands. So if we put that in a worksheet, we got that person's weight, 165, the 25 pounds is the load, and then that horizontal distance, we were saying 15 inches, and we were saying he's bent all the way down at 90 degrees. That puts us at for pounds at 774 pounds. So we're like, all right, we need to do something about that. That's a risk scenario. And it, when we do the Nash lifting equation, you can see this is actually easier than that one, but adding a little bit more personal factors in here. And so if we turn all these numbers into metric, uh, with newtons. So, for weights, won't all be in kilograms. And then that's where that sign is still at 90, but the compression is at 3,200 newtons. So again, high risk. All right, let's do another example. So this guy, that distance from the middle of that back to the source is a little bit further. He's leaning into a box, right? So we asked that subject how much he weighs. We got 170 pounds. The load that he's lifting, these are broilers at 40 pounds. That distance a little bit further from that L4S1 joint to that second knuckle. So we're saying 21 inches. So he's reaching a little bit further. So if we put this, and then we estimate that, bending over. So he's probably about 3/4 bent. So between that halfway and 90, so we're going to say at that 67, 68 degrees. Putting all those values in the worksheet, 170 pounds from the subject. We're saying that load is 40 pounds. The distance from the L5S1 joint to the middle of that second knuckle is at 21 inches. 3/3 bent down at 68. Then all these calculations with Dr. Bernard are calculated. So actually more. And again, that distance from the source is so important because not only are you lifting your upper body, you're lifting that object. So we got to almost 1,000 pounds. If we put that into metric standards, we're looking at 4,200, so quite a bit more than the first example that we gave, and definitely in a high risk scenario. All right, one more example. So this guy, um, just lifting boxes here, a little bit heavier of the guys versus the other two examples. So he's at 220 pounds when we ask him. The load of the boxes at 44 pounds, so just as heavy as the boiler, but heavier than the first example. At the distance from the L4 to the second knuckle here is at 13, so it's slightly closer than the first example, definitely closer than the second example. Let's see how this works out on the Utah compression back. So when we put all those values in, the subject's weight is at 220. Again, that load of the box is 41 pounds. And then that distance from the second knuckle to the L5S1 joint is at 13. So it gives us quite a bit lower than the second example at 885 pounds, but definitely more than the first example. So it's in between those two. So notice how the personal factors probably interplays more on this one than the other two, just for the example, because it's a similar weight as the second example, but closer, but the guy is heavier. So all factors interplaying in this. And then, of course, if we put that in newtons, we're at 4,400 newtons for that example. All right, so I hope you find that the Utah back compression model is very useful. I think between the two, it's a little bit more simpler and adds some personal factors. A really great tool. Of course, we'll discuss the Nash lifting equation, but just one more tool in your arsenal. Please check these out.